All right, y'all. Get started with this stuff. All right, I'm going to run through for the roll. Just give me your first and last names. Thank you, Albert. Thank you, Thank you, John Tell. Thank you, Alta. Thank you, Daryl. Thank you, Mark. Thank you. Thank you, Trinity. Thank you, Kelsey. Thank you, Caitlin. Thank you, Macy. Thank you, Andrew. Thank you, Tanasia. Thank you, Alexa. Thank you, Abdul. Thank you, Roger. All right, y'all. So this problem here, I wanted us to start with kind of a review of what we were working on already, dealing with functions, right? First and foremost, remember, functions are still relations. They're just a set of ordered pairs. The particular function here is the f of x equal to 9 minus x squared. So those ordered pairs follow the pattern of that quadratic, okay? With that said, are we comfortable plugging in, or we need to be comfortable is what I should say, with plugging in to get to some values that we're going to see here? So are we in agreement with those as far as evaluating those first three? Now, which of those is a special result that we should keep an eye out for? Yeah, so they're all points. These are all solutions, but what are some things that we should watch for when we're dealing with solutions? Be careful with our evaluating, right? But just as far as the result itself, we should always be careful of our negative signs, right? So that make sure we got a 5 with the plug-in -2, right? What did we find though when we did this one here? The ordered pair is 0, 9. What is that called? My y-intercept, right? So make sure we keep it. If that's the y-intercept, what's special about this one down here? That is an x-intercept. Now, what happens is since we're working with the function, we found our y-intercept, right? That is the only y-intercept because it's a function, right? For each x, there's only one y. However, we have to be careful, as we kind of talked about yesterday, is that when we start solving these for x-intercepts, it is possible to have more than one solution. Just so happen, plugging in 3, we got one of them, okay? That's where this next piece comes in, though, right? Make sure you see here, that will help us find all x-intercepts, not just one, okay? We don't have to do a guess and check. We can set up an equation and solve. Is there any question, though, with these first three? All right, so as I jump over to the next ones, right, we're supposed to be setting the function equal to 0. How did someone solve that, though? You moved it over to get x by itself. Nothing wrong with that, right? Make sure if you do that, though, that you're careful, again, as we just mentioned, careful with your negative signs. But when you get this here, what must we have? Right, you have to show that there's two solutions. It's not just one, right? Anytime we use a square root to solve, we better end up with a positive and a negative solution there. Now, the other way to solve this would have been factoring, and that would have given you both solutions. Okay. Excuse me. Now, as far as that's concerned, that one, hey, whatever way you're comfortable, do it. As long as we get to the two solutions, we're fine. If you just remember, though, this is the one that we'll run into more often because I might get something like the square root of 2 left over, or I might get a complex number. Now, let's be careful here. To be an x-intercept, can we have I? No, right? So understand that as we deal with this, we might get a graph that looks like this. So if I just do a quick sketch of a graph, right? Is it quadratic? Right? Well, guess what? When you type that equal to 0, are you going to get some real number solutions? Does it cross the x-axis ever? Does everyone see that this will never cross the x-axis? And that's an important thing to see here is know that when you solve, this is where you'll start to see complex solutions come out. So know that like when you do this, you're at some point going to have the square root of a negative number as far as a solution. Now, remember that, show your work to get there, but just make sure when you're done that, hey, I don't have an x-intercept because I don't want complex numbers right now. Is that clear to everyone? So that's one thing to show for. As we talked about the equations, we want to find all solutions, but here we're making a distinction. I want real numbers, not complex numbers. Okay, so keep that in mind. What was going on with this next piece here? What am I doing with this? Right, we're just substituting it in, right? Now, what does that go with, though? Does anybody remember the name of that formula we looked at? It's what we call the difference quotient, right? Remember, it's just the average rate of change, but we use it for special situations, okay? The key here to remember, though, is we got to multiply that out by writing it twice, right? Now, we have that written down already, so I'm not going to write out the whole multiplication again, but just remember as you go through that, write it out twice, do the multiplication. And what we need to be careful of here is what's in front of those parentheses, a negative. So order of operation says I do my exponent first, and then I deal with multiplication. So you have to be careful here with how you handle this. All right. What did I put around the result that I squared? Parentheses. Now, the reason I'm putting the parentheses is because I have something that I need to multiply with that result. Here's a negative. I could put a 2 in front of it. We can make it 2x squared. That would be another example. Be careful with that, right? Square first and then do the multiplication. So with that said, though, this is where we'll see that the distributed negative changing all those signs. I did not mean to put an equal sign. Why did I put an equal sign there? I can't explain that one. Now that's a tough one though, because you have to make sure you remind yourself, hey, this is two steps: square and then deal with the negative. Right? We have to be careful. Now, if you're not careful with that, if we scroll back real quick, oftentimes I find the same mistake with this problem here. All right, there's a reason I said let's plug in -2 because we have to be careful with those signs, right? That, as we mentioned, I was getting more at the intercepts, but watching our negatives is definitely important, right? Hey, -2 squared is +4. 9 minus 4 is 5. That's the same kind of process we're seeing here. Square it and then subtract. Is there any concerns with getting through this that I could help someone feel more confident with? Good. All right. What was the last thing I asked us to find, though? All right. What is the domain of a quadratic function? It's all real numbers, right? Now, this is something that we should get comfortable with recognizing. Linears, polynomials, hey, all real numbers. The domain is all real numbers. What we're going to start working towards is recognizing some of the functions that might have a restriction, right? Which we've kind of talked about a little bit. We do have some that, hey, watch out for some restrictions. Polynomials and linears, we don't have that.
For that one, when we distribute the negative, the parentheses don't stay up there to multiply the 9 times.
It's 9 minus. So once it's its own term at that point. Right. Okay. You're good. Now, keep in mind, like we said, we did this with a couple different functions yesterday, right? I just want us to talk through it again, make sure we're comfortable with it. I used x plus h here, but remember yesterday, I think I did like what 2x or 3 minus 2x or something like that on one problem. I did 3 minus 2x. So this is another example of kind of, be comfortable plugging different things into functions. The x plus h happens to go with the difference quotient. All right. Moving forward, though, there is another thing that we can run into. All right. Excuse me. It's my 4-year-old's fault. I'm definitely blaming the child on this one. Came home coughing. The next thing I know, I'm coughing. So hopefully what you see here is we have relations. How do we know we have relations? We have an x and a y. Is that clear to everyone? We have an equation with 2 variables, so we're working with the relations. No, that means there's an infinite number of solutions here. However, to make things easier for us, we like to keep it in a kind of consistent pattern. So that's why you see here, let's solve for y. All right. Sometimes that's going to be more work than others, but it goes through our same solving skills that we've dealt with that first test. Okay. So here, if you want to get y by itself, what term do we have to move? What happens when we move the 3x though? Do we all feel comfortable with that though? Any concerns here? Now, this is going to be an important one because we've kind of hinted at, we're not quite there yet. We'll be there probably next week, but dealing with linears, we're going to have different ways we need to write stuff, right? And so moving terms around is definitely part of that. But this is also an important part that once you do that, they're like, oh, this is linear, which we could have kind of seen that from the beginning, but this would be a confirmation. What's going on over here? Huh? Is it okay? What's 5 plus -3? What's -3 plus 5? So does it matter the order? Does it matter the order? No. Now, when we get forward into this, it does help because, as I said, as we move forward in this, not today, we are going to get here, right? So that there is a pattern that we typically write. Okay, and that's fine. Nothing's wrong with that. I just kind of wrote it in that order because that's how it was. That's all. Okay. Now, with polynomials and stuff, it's good to have that habit in place. I'm not going to enforce that habit though until test 3. What's going on here though? That's something that makes it different. They're both squared. They are squares, but both terms are squared, right? So we have to deal with this first by saying, hey, let's get y squared by itself. How do we get the squared off the y though? Square root. Now, what is the thing that we have to be careful of here again? Oops. What are we supposed to put there when we take the square root? Plus or minus, which is a little weird now, right? Because we have 2 variables now. So it's very much helpful to write this as it's 2 different parts. Now, let's make sure we see what this means though. All right. If I plug in x equal to 0 into this relation we're seeing, it's still a relation, right? X squared plus y squared equal to 9 is a relation. If I let x equal 0, that's gone, right? Over here, we'll just get the square root of 9 for both of these. But the problem that we run into is how many different numbers does that give us as a result? 2. What number did I plug in? And what variable did I plug it into? X. I plugged it into X, right? Does everyone see that? But how many Y values are we going to get back? 2. What does that violate? For each X, 1 Y. So there's nothing wrong with this relation, but this relation is, it's not a function. Now, you didn't actually have to plug in the 0. Just know that when you get here, that's kind of your hint that I just have 2 different solutions for y right now, which means it's not a function, right? What you're going to find here, this is actually a circle, the equation of a circle. And both of these would be like the top half of the circle, the bottom half of the circle. That's where that kind of comes from. Now, with that said, though, hopefully you see here, if I ask you to solve for y, I'm probably going to ask you if something is a function. If it's linear, yeah, it's a function. If you have to take a square root to solve, oh, this is definitely not a function, right? Now, we do have to be careful because there will be some other ones that you want to make sure to have different skill sets for. We don't necessarily go into all of them, but I would say right now, if you see a y squared, show your work for solving for y and then know from the beginning, oh, it's not a function because that's going to be plus or minus. We go with that? That goes back though to, hey, if I see something squared, I should be expecting 2 solutions. All right. Now, here's 2 examples, though, of functions where we do want to be kind of prepared to watch for stuff. The other one, the x squared plus y squared equal to 9, I would just put, hey, circle next to it so you kind of remember moving forward. We will look at that further at the end of the semester. But as I mentioned with that quadratic, we should be comfortable with, hey, it's quadratic, my domain's all real numbers. What type of function is g of x, though? Here. Square root, good. In general, you could call it radical if you want. But a square root is the specific radical we're working with. What about h of x? What do we call that? Huh? You said rational or fraction? It's rational. Is that clear to everyone? This would be where we go back and say, hey, this is rational. Now, with this, though, what's the first thing I should do when I deal with a ration? Anytime we have the fraction involved. Right? This goes back to our test, right? That we said, hey, if I have a fraction and the denominator has a variable in it, the first thing I should state is what? The denominator cannot be what? What number cannot be in the denominator? But what number cannot be in the number can't be 0, right? Now, we can't use 5, though, because that will make it 0. Is that clear to everyone? Now, is there any other number that we'll run into issues with here? Is there any other number that when you subtract 5, you get 0? What's negative 5 minus 5? So do we need to worry about that one? That's a good one to think about though, right? It's still 5. At this point, that's the only number that will cause an issue, right? So what we need to see here is say, I can use all real numbers, just not 5. So writing x not equal to 5 gets directly to the point. Interval notation, know that that gets a little bit more complex because we need to show that it's still all real numbers, right? That's where negative infinity, positive infinity come into play. But it's weird because you have to say every real number less than 5 and then every real number bigger than 5. You have to break it up into 2 different things. What part? The middle? It's a union symbol.
We can't use a bracket for our answer.
Were you doing increasing and decreasing?
When we do our order pairs and we try to close, like we do negative infinity, comma 5, close bracket, it won't allow us to do that. So if we keep putting the,
You need to show me the problem. That's
I'm gonna take a picture of it.
yeah, please do that. Because I don't know if it's the problem or if there's an error on the coding side.
They have it, but you'll have to.
The one thing I will say with some of those, know how to get your keyboard and find that stuff on there because sometimes the toolboxes are not good, both on Pearson and on My Open Math. Their toolboxes do have limitations. Okay, so that could be the issue. That's why I said send me a picture so I can see. All right. That's just one of those recommendations that, but if you're on a mobile device, you're not going to like an iPad. It's going to be I still don't know how to pull up my keyboard when I need it on here. So I'm all the way up here. I got my distance now. All right. So why is the negative infinity and positive infinity important in the interval notation here? It's all real numbers. What number is repeated twice there with both those intervals? 5. And what you're seeing there, the 5 is repeated and there's parentheses, right? So we're saying every number, just make sure you don't use that one single number. Okay. Now make sure you see here, there's 2 different ways to write it. That's that set notation where you see x cannot equal 5. And then the interval notation is what we see here at the bottom. And that's going to be what I expect on tests, though, is make sure you understand that the interval notation is what is expected. Okay, now the homework, if you see set builder notation on Pearson, make sure you put x cannot equal 5, because that's the whole focus of both of them. Okay, now what's different about the square root? I picked the rational first because that's one we talked about, and I tried to make sure to get that out, but very few people right off the bat wrote the denominator can't be 0. Right? Huh? We're not trying to yeah. What is it about square roots that we're trying to avoid right now? We don't want imaginary, so we don't want what? Negatives, right? So what we want to show here is that, hey, x plus 3 cannot be negative. Well, what number separates positives and negatives? 0. And what number are positives greater than or less than 0 at that point? So what we want to show here is that x plus 3 has to be greater than or equal to what? 0. Now, the purpose of that is we're saying it's non-negative. It can be 0, it can be a positive number. We don't want negative numbers. Well, guess what? Solve that again by subtracting the 3 from both sides. And this one goes back to our inequalities that we talked about, which is nice, right? The set builder notation tells us exactly what we need. -3 and bigger, that's it. I can plug in -3. I can plug in -2 and so on, as long as I'm getting bigger. The other nice thing here is as long as you're comfortable with your graphing of a number line, all right, as long as you remember your number line that, hey, that 0 is definitely bigger than -3, right? We're putting that bracket or closed circle here, whatever you're comfortable with, and we're going up from there. So our interval notation will be -3 to positive infinity. Questions or concerns? Yeah. Huh? From this statement here. The second you see you're working with a square root, this is not, we don't want it to be negative. We don't want imaginary stuff right now, right? So that's where we take whatever's under the radical and we say, hey, this has to be greater than or equal to 0. So it's this statement that we need to make sure that we're starting off with right away. The same way over here with rationals, that's the main thing we're focused on. Denominator can't be 0. If x is greater than it, yeah, the number will go first. Just be careful. Remember, I can write this differently. And we could see that, hey, the greater than part's pointing towards the x. So that's why you want to be careful. Now, that doesn't happen all the times. When I like to do stuff like this on a test, that way we're being careful when we solve here about what symbol. The negative, right? When we do that division, we have to remember to change the sign, which a lot of you did fine on that last problem, but several of us, when we divided by a negative, we did not switch our sign. So we have to be careful. That's good. All right, so the next thing I want us to do is look at a couple graphs. Now, I don't think we're going to have time to finish everything. So what I want you to do is make sure you write these 6 down. All right. As far as dealing with these, though, what we're really wanting to do is go through here and be like, look at this from the perspective of like, hey, this is a linear, this is a quadratic, and so on. Make sure you're able to name them. Make sure you're able to identify the domain. You're going to need to graph it to get the range. Okay. Graph it to get the range, and then determine if that relation is a function. Hopefully what you see here, though, I'm trying to get you to learn different kinds of functions, but make sure you remember, how do we test for a function, right? They're already solved for y, so solving for y isn't going to help us, so we need to graph it and use what? What was the test we used with a graph to determine if it's a function? Vertical line test, right? Now with that too, I'll be comfortable with identifying the intervals of increasing, decreasing, and constant. All right. That's another thing that this is just more practice with doing all that. My main thing that I would hope we can get done today is go through and graph all 6 of them. So that's what I'm going to focus on, but make sure we're also comfortable doing all the rest of the stuff. Okay. Because time wise, I think we're only going to be able to get the graph stuff. Now, on my end, thankfully, I already have the coordinate planes in place. So what's something that stands out to someone here, though, as I get ready to plug in values? What did I use for all of these? Yeah, -2. So when I go to the other ones, know that I'm going to take a similar approach, except for the square root, right? And then we're going to look at that fraction one, because those are the ones with restrictions, okay? But hopefully we'll see here that when we go to start deal with this, when I plug something in this first one, I get the same thing back. All right, it is linear. This one, you might see something called like the identity function, because whatever you plug in, you get the same exact thing back. What should our graph look like, though? Does everyone agree with that? Something along these lines? Any concerns with graphing a linear? Make sure you see here, though, we should expect domain and range for both of them to be all real numbers. It's always increasing in this case. Okay, it could be decreasing in other cases, but this one's always increasing. Is it a function? All right, passes the vertical line test. Okay. Part B, though, we have looked at this one, so hopefully we're comfortable recognizing it, but make sure you're careful again with your negatives. Oops. Huh? Things to look at here, though, is make sure you see that the range is restricted, right? We didn't get a negative back because whenever you square something, the result's always going to be positive. A negative times a negative is a positive, right? If you remember, this is also an example of that symmetry. So this would be considered an even function because it's symmetrical to the y-axis. Okay. Do we feel comfortable getting those points, though, and getting the graph? All right, so moving on to the next one, be careful here, though, because what the difference is we're going to see similarities with the quadratic over cubing now. So when you cube, the negative actually stays with whatever we're working with. So -2 cubed is -8. With that said, though, there's a similar curve to it. It will be a little bit more in the steeper side, though, because we're cubing rather than squaring. But there's going to be more of an S shape, too, because of that. All right, one thing I would point out here, this is what we call an odd function. And that's because it's symmetrical to the origin. So when you see that, this is where we see symmetry to the origin. And the best way I could say to look at that is like if I come over here to mess with this graph, if I turn it upside down, what happened? So everyone see how same graph? Now we can see it's turned upside down, right? Because now -5's at the top, 5's at the bottom, but the curve itself is the same. All right, so that's one of the nice ways about looking at that from that perspective. Okay. Domain and range, very similar to the linear. What you'll see there is linear is also odd, right? When we look at y equals x and y equals x cubed, they have similarities. The difference is the curve that a cubic brings, right, for polynomials. All right, so moving on these next ones, though, what is the special case that I need to be careful of here when I look at the square root? Right? Do we want negatives? Right? We don't want negatives. Now, what else did we say we want to watch for to help make it a little bit easier for us when we start plugging in values? Did everyone hear that? So we'll start at 0 now. We'll plug in 1, and after 1, though, what should we plug in? 4, and then we could plug in 9, 16, 25, and so on. Now, keep in mind, practical-wise, usually I try to do stuff within -10 to 10, so there's no point in doing much more than that. But make sure you see here that when you do the square root, we should see that pattern of 0, 1, 2, 3, 4, or whatever shift or something that might be involved. If you also remember, this is one of those, it's got a kind of curve shape like a quadratic. It just happens to be on its side. Any concerns with that one? What was special about absolute value? Does anybody remember? It is the distance from 0, right? So when we plug in 0, 1, and 2, we get that same value back, right? What's the absolute value of -1 and -2, though? Goes back to the positives, right? So all of a sudden, we see some repetition of values, okay? With that said, our graph should look something like this. So what shape should we expect with our basic absolute values? A V shape, right? We all good with that? Now, like I said, all we had time for was to do this. Some of these we had already done. However, this one is one that we do have to be careful with. What is going on with this last one that we must keep in mind? Right? Can I use 0 here? Does everyone understand why we can't use 0 here? Right? So we do not want to use 0. All right. Now we can go in and plug in the other values. What you're going to find here, though, is this is what they call a reciprocal function. Because you put 2 in the denominator, you get 1/2. If you put -2 in the denominator, you get -1/2. So it's kind of the reciprocal of what we're working with. With that said, though, an important part when we deal with rationals is to get as close as we can to that value that we can't use without going through it. All right. What you're going to find is it's going to have a big impact on the graph itself because I cannot plug in that value. So what I recommend always doing is starting kind of by putting a line that's not really a part of your graph, but it affects your graph. And we'll go into more details with this as we go through different stuff. However, we do want to make sure we get as close to it. So for this, let's just use -1/2 and 1/2. We could get closer, but that usually is enough to see what's going on. But what's the reciprocal of 1/2? 2/1, or we could just put as 2, right? And the same thing over here, but it would just be negative. With that in place, we could start to see a curve that takes place with these values we're plugging in. All right. Now, it's not perfect as far as a graph is concerned. And we're just trying to take a basic approach to this. Okay, so please keep this in mind. We're just trying to do a basic, quick approach. My main thing that you should take from this is don't forget your restrictions. All right. Because what happens here, as I deal with this graph, I'm going to get really close to that, but I'll never actually get to it. But instead of having one line, how many lines am I drawing right now? 2. And this is special, though, because of the rational thing we're working with. What you're also going to find is, as I put that vertical line, there's also a horizontal line that we got to explain as well. Right? Because as I can't plug in 0 for this problem, there's no way we could get 0 back. All right. The main thing I would say is be careful with this one is just remember the denominator can't be 0. And whatever your restriction is, make sure you kind of focus around it. Don't plug it in, but see what happens as you get close to it. All right. That's always helpful as far as making sure we get the correct kind of turn that takes place. Now, the other 5, be ready to grab those at any time. This one, like I said, you might have some of these on homework now, but we're going to go into more details with this with the 3rd module when we focus on rational functions. Okay. Any questions, concerns with these as far as the graph is? Now, remember then to also go through and deal with the domain, the range. Make sure you see all of them are functions using the vertical line test. And then make sure you're able to identify the intervals of behaviors as far as increasing, decreasing, and constant. All right. I would on your way out, come get your test from me though.